Hi everybody. As we're progressing into our spectral analysis, I wanted to show you a real-world example of how to do some of the problems that we're going to be doing. So over here on the right you can see a problem that gives us IR, mass spec, elemental analysis, and NMR. Sort of a real-world compilation of the different materials that you might have available to you in a lab analysis of an unknown. And I wanted to show you sort of the idea of how we'd work through this. For me, the first thing I want to look at is the elemental analysis. Some problems will give you a formula just straight away. Some will give you an EA analysis like this. And if we're given elemental analysis, we just have to remember from Gen Chem how we should go about doing that. So what we've got here is 80.5% carbon, which in a 100 gram sample we could say is 80.5 grams, 10.1 grams of hydrogen, and 9.4 grams of nitrogen. Back in Gen Chem we learned that if we wanted to develop an empirical formula, we would divide each one of our materials to make them into moles using their masses from the periodic table. And when we do that, we're going to get some numbers. So 6.7 here, we get 10 here, and we get about 0.67 here. And then elemental analysis, empirical formula determination would say we divide each one of these by the smallest of the answers, the 0.67, to normalize. And what we're going to end up getting when we do that is we'll get something like 10 for carbon, something pretty close to 15, and something like 1. So our empirical formula is C10H15N. We're also given in this particular problem the molecular weight, 149. And if we add up all the pieces here, 10 carbons, it's about 120, plus another 15 for hydrogen, 135, plus another 14 for nitrogen, that is our 149. So we know this is actually, in addition to being our empirical formula, this is also our molecular formula. So we know now that our problem is C10H15N. The next thing we want to do is to figure out how many degrees of unsaturation we're dealing with. And this is covered in the Klein textbook at the end of chapter 14, where he talks about hydrogen saturation. I talked about it in Organic 1. What we'll be doing is converting this by taking care of any halogens, oxygens, or nitrogens. The rule for nitrogen in this case says that we take away one hydrogen for every nitrogen that's present. So the sort of equivalent or comparison formula would be C10H14. If it was completely saturated, we know the rule says that we have 2 hydrogens for every carbon, plus 2 in a fully saturated molecule. And so our C10 would have to have H22. The difference then is that we're missing about 8 hydrogens, or 4 degrees of unsaturation. Now remember, a degree of unsaturation can be a pi bond, like in a double or triple bond scenario, carbonyl, a ring. It could be, in this case, when we have 4 degrees of unsaturation, I like to think about an aromatic ring, because that gives us now 1 degree of unsaturation for the ring itself, plus 3 more. So that's a pretty easy way to get us 4 degrees of unsaturation. If you do a problem that gives you 4 or 5 or 6 degrees of unsaturation, consider an aromatic ring. It's a really good first step. So let's consider that we have an aromatic ring. in our molecule. That takes care of 6 of our carbons. We still have 4 carbons, a bunch of hydrogens, and a nitrogen to figure out. So let's get rid of this elemental analysis stuff, because now we know the answer for that. And as we look over at the data that's given to us, we have mass spec, we have IR, and we have NMR. And hopefully we've got handy somewhere our tables from chapters 14 and 15 that will help us with our chemical shifts. But for right now, we're starting to build our molecule, and I am presuming that we have an aromatic ring in there somewhere. Now my next step would be to look at the IR to find out what functional groups we have present. And specifically, I'd like to find out, do I have any double bonds? Do I have any triple bonds? Do I have any alcohols or amines or any of those easy to identify groups? In this case with a nitrogen, I'd be looking for amines, of course, and I see that. Amines show up around 3,500 along with alcohols. Alcohols tend to show up as a big broad peak, and of course we would need an oxygen to even consider that. Amines show up as sharp peaks, and the cool thing is you have 1 peak for each hydrogen on the nitrogen. So since I have 2 peaks here, I know that I have an NH2 group someplace. If I had an NHR, so a secondary amine, that would show up as only 1 peak. So I know coming off of my aromatic ring somewhere, I have an NH2 group. If we look down below at the proton NMR, I see that NH2 group showing up as a 2 hydrogen peak around the 3 to 5 kind of region where alcohols and amines show up. Now what I also see here is a couple other things missing. So now I know I have the NH2 group. I know that I've got 6 carbons already taken care of with my C6 ring. I need to figure out where the other 4 are. In order to determine structure, my third step would be to go down to the carbon NMR. And what I'm going to do on the carbon NMR is look for how many signals I've got. And here I've got 1, 2, 3, 4, 5, 6 different kinds of signals. And what I'm seeing here is that 4 of those kinds of signals are pretty far to the left. They give me pretty high shift values. Those are going to be my aromatic ring carbons. Well, that only leaves 2 carbons over here, seemingly. I've only got 6 carbon signals, but I know that I have 10 carbons altogether. I must have some symmetry. And so probably what that means is that whatever group is represented over here, I actually have 2 of those. It would make the most sense, be the simplest, to consider 2 ethyl groups here. That would give me a CH3 and a CH2 kind of a peak, and those shifts are approximately right. If I look up at the proton NMR, I also see that. I have 2 CH3s here and 2 CH2s for 4 hydrogens and 6 hydrogens altogether. And so what I know now is that coming off of my ring, I also have 2 CH2, CH3, 2 ethyl groups. So now my only concern is, how do they line up? What's the arrangement here? Because now I've taken care of all of my atoms. I've got 10 hydrogens, 10 carbons, 15 hydrogens, and a nitrogen. So when I start to look at my possibilities, I know that the 2 ethyl groups have to be symmetrical relative to one another, because otherwise they wouldn't line up perfectly over top of one another on the NMR spectral. So I could imagine that I've got the amine group at the top. Maybe I've got my 2 ethyl groups sticking off like this. That would give me the symmetry that I need to make everything line up. Or I could imagine a similar molecule with my ethyl groups coming off closer to the nitrogen. So that I can analyze this properly, I'm going to go ahead and fill in all of my additional hydrogens that are missing from the picture. These two hydrogens are symmetrical, and so I would expect to get only one signal from those guys. And then the other hydrogen on the ring is different. So how can I distinguish between these two? Because they would give me exactly identical IR readouts. They would give me very similar carbon NMR readouts. What I'm going to be looking for is proton NMR splitting. So on the proton NMR, I've already dealt with my ethyl group and the end here. So I can say these are from my ethyl groups. I've already dealt with my nitrogen, which is my amine group here. Now I have to deal with these two highly shifted values. What you'll see when you look at the proton NMR tables is that pretty much the only thing that shows up at a delta value between 6 and 8 or so, 6.5 and 8.5, are aromatic ring protons. This is showing me the one hydrogen in one place and two hydrogens in another place, which is what I would expect. But what I want to look at is the relative positions of those two. So I know that these guys are from my ring, but I need to know how they work. And what I want to point out is two things. One is the relative shift. The fact that the two hydrogens are shifted further than the one hydrogen suggests that those two hydrogens are closer to the nitrogen, closer to the amino group. Now in both of my pictures, the two hydrogens are closer to the amino group. I listed those in blue. And the one hydrogen is further from the amino group. It's going to be slightly less shifted. And that's in red. Now when I look at the splitting, this is what's really important. The two hydrogen peak that I showed in blue here is split into a doublet. That means that those hydrogens each only have one neighboring hydrogen, whereas the one hydrogen peak is split into a triplet. That means it has two neighboring hydrogens. What these two pieces together tell me is that whatever hydrogens are causing the two hydrogen peak, they're exactly adjacent to the hydrogen causing the one hydrogen peak. They're next to each other. And that is the primary driver that tells me that this is the correct structure. If I had had the structure up above, then all three of these hydrogens would have shown up as singlets because they don't have any neighboring hydrogens. The shifts might have been a little bit different, probably would have been a little bit different, but the really key indicator is that we're talking about that doublet triplet pairing. It's the same thing when I looked at the ethyl group that told me that this altogether was involving an ethyl group. It's because I had 4 hydrogens here being split into a quartet, meaning they have 3 neighboring hydrogens each. And I had 6 hydrogens here being split into a triplet, telling me they have 2 hydrogens each. That's really characteristic of an ethyl group, where I have 3 neighbors to split those guys and 2 neighbors to split those guys. All of this taken together seems overwhelming when we start. And we're just looking at a blank page with all sorts of squiggles and peaks and splits and everything else. But the process that we've gone through here is one that you can use and that will pay off for you most times. You're going to be looking at the formula or creating a formula from elemental analysis if you need to. You'll be looking at the IR spectrum to determine which parts of the molecule you have, how those atoms are used. Do I have carbonyl groups? Do I have amines? Do I have alcohols? Whatever it might be. You look at the carbon NMR to find out about symmetry, sort of gross structural features, and then use the proton NMR to really drive home which one of the molecules is true. I'll have lots of practice at this, but I hope this walkthrough helped.